Welcome everybody. So last week we saw how to compare cardinals, how to say when two sets have the same size, to compare sizes. To say, but we only define how to tell when two sets have the same size. Now we want to talk about when is that we can say that one set is larger than another in terms of size. Okay, so the definition we're going to use is this one right here, and this definition says the following. So we said that a set A is dominated by a set B, and we write A little squiggly less than or equal B, if there is a one-to-one function from A to B. Okay, so that's all we are assuming. So essentially, here is one-to-one function, and the one-to-one function has some image, and essentially this one-to-one function f is a bijection A and the image of A, which is inside B. Okay, so that kind of makes sense. That would mean that A has a smaller size than B. Okay, so that's what it is. It's a one-to-one function from A to B. We say that A is dominated by B. So dominated means that B is larger. So a couple of simple, this is notation. So we say that in the case when we're talking about cardinals, we say, we just write less than or equal instead of the squiggly less than or equal. If these two guys are cardinals, we just write this cardinal is less than or equal that cardinal. Okay, so remember the cardinals are these particular objects that are representing all the different sizes. So when we're talking about one of these sizes, we just say less than or equal. We don't need to use the dominated by. And in particular from this definition, when we have that A is a subset of B, then A is dominated by B, of course, by using the identity function, or the inclusion function, I guess it's called, when it's a subset. So if you're a subset, then you're clearly included in the other, right? So, for instance, we have that the natural numbers are a subset and therefore are less than or equal size of the integers, less than or equal the rationals, less than or equal the reals, dominated by the complex numbers, right? So actually we know that these three sizes are going to be the same, and we saw in class last time these two sizes are also the same, but so far, yes, so we know those are the same. But right, that's the inclusion chain that we get right there. Let's see a few examples. So here is a bunch of equalities and, well, inequalities, let's say, with this domination relation. So let's see what we got up here. So the first one we did in the last videos, right? Remember, it's a video when we show this one. So the tangent function gives you a bijection between an open interval in the reals, not that interval, but some open interval in the reals and the whole real line, and then you get a bijection between those two. This one is clearly a subset of the intervals, the closed interval 0, 1. Okay, so that's an easy one. What about this one? This one is a pretty interesting one. Why is that? I'm saying here that the interval 0, 1 in the reals is dominated by the power set of the natural numbers. So to show this, we will need to define a one-to-one function from 0, 1 to the power set of the natural numbers, right? So a one-to-one function from 0, 1 to the power set of omega. So how do we define this function? And the idea is to look at the binary representation of the number. Consider this binary representation. So a binary representation, remember, is when you write the number r in base 2, so it's going to be of the form 0 dot, and usually have all the digits after that. Let's call them b0, b1, b2, b3, b4. But now these digits are in base 2. So for instance, 0.1100111001. This is what it's going to look like. whatever the number is. And the same way we can represent numbers in base 10, using the digital expansion, we can represent them in base 2. And what this means is essentially that it can be represented as a sum of powers of 2. If bi is 0, then we don't put the power. If bi is 1, we put the power, right? So that's the binary representation of a number. Yeah. So okay, so there is an issue with binary representations. There is an issue with these two cases, right? So if you have a number that ends with 1, 1, 1, 1, 1, 1, 1, 1 forever, it's the same as the number that has the 1 in this position and then it ends with all zeros. The same way as when the digital expansion, when you have a number that ends with 999999999 from some point on, that is the same thing as just adding 1 to the next digit and then having all zeros, right? So number 1 is the same as 0.999999999 forever. That's the same as number 1. So the same happens in binary. So we have to be careful with these two. So we have to decide. These are two representations for the same number, right? They give you the same number. So we have to decide on one. So choose a representation that doesn't end in all ones, right? So we want to eliminate this case, and we just leave the other one. So whenever you have actually it's a binary rational that we can write in these two ways, just choose the one that ends with zeros. Well, unless you choose 1. So unless r equals 1, in this case we choose 0.11111111111. That's the one we choose. We choose this one only for the case of r equals 1. Okay, so you do that. So now every number has a binary representation. And now how is that we do that map into the set, power set of omega? Well, we just say, so now h of r be the set of all the i's in the natural numbers, such that if you look at the binary representation of r, bi equals 1. So in some cases we get 0, in some cases we get 1. For some digits it's 0, some digits are 1. So choose the digits that are 1. Okay, so h is a function that for each number between 0 and 1 is going to give us a subset of the natural numbers. It has to give us a different number, right? Because given, if you know which ones are 1s and which ones are 0, we can recover the number back. So h is 1 to 1. Yeah, so h is 1 to 1 because if you have different numbers, you can have the same binary representation. Is it onto? Well, it's not necessarily onto, and that's why we don't have here the equinumerous sign, because since we had to choose between one of the representations, we are leaving out some subsets, right? So we are leaving out the subsets that end with having all the elements in, so having all the elements 1. So those are not in the image of this map because we chose to use this representation and not to use that representation. Well, if you had chosen the other one, we would have left out these ones. So one way or the other, we're leaving something out. So this map is not onto, but it is a one-to-one map. So we do get that this one is dominated by power set of the natural numbers. So how is that the power set of the natural numbers, set of all the subsets of the natural numbers, is equinumerous to the set of functions from the natural numbers into 2. Okay, so remember, this is a set of functions from the natural numbers into the set that contains 0 and 1. Here, the set of all the functions f's from omega to 0, 1. So how is that we get this bijection? So we want to define, let's call it h, from omega to the power set of omega. So we want to define a function that that maps every function from omega to 2 to a subset of the natural numbers, and we want it to be a bijection. What is the function? Given a function g that belongs to the set of functions from omega to 2, so let h of g, right? So notice that g belongs to this guy, and now we want to define h of g that belongs to this guy. So this has to be a subset of the natural numbers. The set of all the i's such that g of I equals 1. Right, which is sometimes we can write these as g inverse of the set 1. So this is 1-to-1 because if you have because two different functions, the functions are determined by which numbers go to 1 and which numbers go to 0. So having the set of all the things that go to 1, then we know which ones go to 1, those that go to 1, and then the ones that are not in the set go to 0. So the function is determined by this set, so it has to be 1-to-1. And it's onto because for every set there is going to be a function whose all the elements in that set go to 1 and all the elements in the complement go to 0, right? So this function is going to be a bijection. So essentially these two guys, power set of omega, subset of natural numbers, and functions from omega to 2 are almost the same thing. They are not the same object, but in logic we often look at them as the same thing. Essentially this one, for each, so elements of the power set are the subset of the natural number. For each number you have that the number can be either in or out. When you have a function from the natural numbers into 2, you have that for every number it can be 0 or 1, the image of the function. So in or out, 0, 1, these are two different ways of kind of the same thing, just two possibilities. In or out, you use this one, 0, 1, you use this one, right? So those two are the same. Okay, and what about the last domination over there? Well, what we have in here is, so consider the function from the set of functions to R be defined by the following formula. So that's given a function g from omega to 0, 1, that's the same thing as saying g belongs to 2 to the omega. We let h of g, we are supposed now to get a real number, right? So we took a function here and now we want to get a real number. So what real number are we going to choose? We're going to choose the sum of g of I times 3 to the negative I. So essentially now what we're doing is writing a number in base 3. So h of g is going to look like something of the form 0.011010 because g only contains zeros and 1, but viewed in base 3. Why do we use base 3 instead of 2 if we only have zeros and 1s? Well, because of the same issue we had before, that we don't want to confuse these two guys. We want our function to be onto. So we don't want the function that gives you all 1s and gives you all zeros at the end to give you the same number. We want them to give you different real numbers, right? So we want our function to be 1-to-1. So we don't want those two to get confused. So then we use base 3. In base 3, there is no confusion because the ones that are equal here are the ones that end with 2, 2, 2, 2, 2, 2, 2, 2. Those are the ones that get confused with the ones that end with 0, 0, 0, 0, 0, 0, right? So here this one is 1-to-1 and is the embedding that we want. Okay, so we have that the real numbers are dominated by 0, 1, power set of omega, functions from omega to 2, and then back to the real numbers, right? So you would say, well, that means that they are all the same. Yes, it does. It's going to mean that, but this requires a proof. It's not a trivial proof to show that from these being sandwiched in between the reals, we have that they are all equinumerous. So that requires a proof, and we're going to see that in a couple of videos. See you guys later.